So, okay, so this is the summary. So the people online, you don't miss anything. So this is just the summary of the process. I think there's a bit of return very close. Okay, so this is where we are now. So there are 3 missions. So you know well, because one of them actually is from here, right? Plasma Observatory. The other one is Theseus, which is also the PI is also here in Italy. And the last one is Matis, which is me, in this case, the PI. But also with enough participation with Rafaela and actually Anna, Valeria, and other people here. So, okay, so what is the concept behind that? So why we are proposing a mission to Mars for this characteristic? So it's really how to say, I want to say it's not just a Mars mission. It's not a Mars mission because, I mean, of course it's Mars because we go to Mars, but it's a plasma mission. And that's a very important difference because we are really focusing on understanding the evolution of the atmosphere and the plasma, while many of the missions that are at the moment planned for Mars, they are really focusing on habitability, but seen from the surface, what happened at the surface, processes, geophysics, basically. So it's not just a Mars mission, it's really a plasma mission, and that's very important for us to explain to people. So we really want to understand, it's very important for us to understand and quantify the energy flow to the system, but especially focusing on the temporal and spatial variabilities, because so far we have single observations, and that's absolutely impossible to know if something that you see in the data is a temporal evolution, or is spatial variability, or is something that is there and that's it. It's not possible at all to do that, and we have that experience from Earth, that you really need multiple satellites and multiple observations to do that. So when talking about the energy, how it flows in the system, so that's why we have the figure here on the right. So if you focus on the panels that are towards the left, so this is mainly the neutral part of the atmosphere. So from the surface at the bottom, so hopefully you can see here, from the surface at the bottom to the middle atmosphere, which is not included. Sì. Okay.
Allora torno di là, prego.
Scusi.
Prego.
Non so se ho finito completamente dalla sua parte.
It's okay now, right? Okay.
Sorry, could you mute your microphone?
Okay, good. So we have the thermosphere, which is where it's a critical region for us. So this is about 100 kilometers altitude. And then we have the exosphere, which goes beyond, I mean, it's the upper part of the atmosphere, but also goes beyond the actual planet. And then on the right of the figure, so we have the ionized part, with starting with the ionosphere here, at the same region of the thermosphere, so they are together, and above we have the magnetosphere. So these are the different regions of the system, and then you see all these arrows in here. So in black, we have the transfer of energy. So you see there is 2 main sources of energy. So one is the solar wind, So one is the solar irradiance, so the sun. So this goes deep into the atmosphere, affecting all the layers. But also we have the solar wind, which has a strong interaction with Mars, as we will see soon, because there is not there is not intrinsic magnetic field. So the goal of us is to understand all these couplings. And that's why we call that the MIP, because this is the coupling between the magnetosphere, the ionosphere, and the thermosphere. So this is really the concept, which is actually is what we do at Earth, what we are doing on other planets. Hopefully we will do the same at Mercury when Baby Colombo arrives, because there are 2 spacecraft. But we are lacking that of Mars. So that's why we decided to propose a mission for that. So this is actually quite complex. You will see that soon in a few slides, but it's actually key to understand the evolution of Mars atmosphere. It's really the key. So you can understand what happened in the past by looking to the surface, by looking to water at the surface, by looking to how the winds move. But you cannot understand what happened to the atmosphere, to the fate of the atmosphere, if you don't understand the plasma and how it interacts with the solar wind. So it's actually essential. But it's more, we know a lot from the mission that we have, but we really need these multiple observations. So that's why we need at least 2 satellites. And with that, we can actually start uncovering the fate of the atmosphere, but which is also more important, so we can prepare for the future. So there is a lot of exploration planned for Mars. There is not only for robotic exploration, but there are really serious plans to send people to Mars. I mean, in my opinion, you cannot send someone to Mars and not count into account how the radiation is absorbed in the system. It's essential. So it's a science mission, but also has strong influences, and it will have significant impact on other directorates at ESA. So we have 3 goals, which I will develop now one by one. So just as I said before, is just to understand this MIT coupling. So the first goal is focusing on the system as a whole. So this is really global dynamics from the surface of the planet up to full space, so covering all the system. I've put in here 2 examples of 2 simulations in which you can see, I mean, we will see that more in detail now. You can see actually that this is much more complex than you can expect from the beginning. The second goal of the mission is to understand the radiation environment. So this is how the atmosphere, how the ionosphere actually absorb the radiation that comes to the planet, or sometimes it does not absorb the radiation, sometimes goes directly to the surface. So that is actually the first step toward forecasting weather at Mars. And also the coupling with the lower atmosphere, so the coupling of the atmosphere near the planet, the surface, with the lower ionosphere. So this is actually quite unknown because we don't have direct observations of the region. And it's very, very important to understand because this is where actually the auroras are formed, where we have communication problems when we transmit in HF. So this is a region that we have to explore and understand. So that's why it's included as one of the main goals of the mission. So we'll go now one by one, but please, if you have questions, just ask. Like, I don't want to be talking alone. If you have any questions, just please interrupt and ask. So going to the first goal, so the system. So this is a nice sketch that ESA made a few years ago for the interaction of the sun, of the solar wind, so that's the sun with the solar wind with the different planets. So you see that actually Mars, if you compare that to Earth or to Venus, is the smallest one because the planet is small. Also, the atmosphere is quite thin. So it's thin, but it's interesting. So interaction is small. However, the interaction with the solar wind per se is perhaps more complex than for Earth and Venus in the sense that we have crustal magnetic fields at the surface, which are stronger than the magnetic field of Mercury, just to give you an idea of the magnitude. So they can actually produce an extremely complex interaction with the solar wind. So this is what we know is happening. So there is a region in the tail which has never been explored, and we plan to, with our orbiters, we plan to go there and explore that region. But also all the areas and everything that you're seeing here. So in yellow, you have the ionosphere, and then you have in pink the magnetic pillar boundary, which will be the equivalent to the magnetopause at Earth. And then in green, you have the bow-shock, which is the first boundary. And then all the arrows and everything. So there are different processes that we know they're happening, but we don't know their scales. We don't know their evolution with time. And this is the key for us to understand. Just to give you an idea, so I know this is perhaps quite basic, but this is actually how Mars interacts with the solar wind compared to Earth. So you have Earth on the left. And of course, I assume everyone knows how Earth interacts with the intrinsic magnetic field. So we have an intrinsic magnetosphere. And we have an indirect coupling of the solar wind with the ionosphere because we have the magnetic field in the middle, and there are field aligned currents joining the magnetosphere with the ionosphere. However, at Mars, in principle, if we forget about crustal fields for now, so there is no that intrinsic magnetic field because Mars lost the magnetic field many millions of years ago. So the interaction is a direct one. So because the solar wind directly interacts with the atmosphere. So there is attached, the ionosphere is like a kind of a sponge in there, absorbing everything that comes from the solar wind. And the interaction is, of course, much closer to the planet because the standard distance, we don't have the magnetic field like Earth to protect the planet. So whatever, even, how to say, a very fast stream in the solar wind, which in principle should not create major problems, can has strong perturbations of the magnetosphere of Mars, simply because the interaction is much closer to the planet. And in principle, that is the same for Venus. But in the case of Mars, in the southern hemisphere, hopefully you can see here in these scales. So we have these crustal magnetic fields. So they can be thousands of nanotesla. Just to give you an idea, Mercury's magnetic field is 400 nanotesla. So they are really strong fields that actually can touch the solar wind and can reconnect. So imagine the Darby cycle that happens at Earth. It happens all the time at Mars because the crustal fields rotate with the planet. So it happens all the time. And I guess that's why Marco and Andrea, you many times don't see the signals from Marsis because they are extremely perturbed by the crustal fields and the particles that are traveling through the crustal fields. So this is the general interaction of the planet, like in basic, and this is the ionosphere, and a sketch that I made for a white paper a few years ago. So on the left, you have the day-side ionosphere. On the right, you have the night-side ionosphere. So in black, this is the typical electron density profile that we should expect. So the main layer is about 140 kilometers. It's like the E layer at Earth, very similar to the Chapman layer. On the night side, the layers are more sporadic, but you can see that there is a lot of variability above and below, and this is because Mars is small, but it has volcanoes of 30 kilometers altitude. So the Everest is only 8 kilometers. So imagine there are 4 volcanoes about 30 kilometers altitude. So they create strong gravity waves. They create a lot of perturbations into the atmosphere, and this has an effect also on the variability of the bottom side of the ionosphere of Mars. But at the same time, we have the sun, we have particles coming from the solar wind, and you will see that later. So they produce also a lot of ionization in the upper part of the system. So this is like the sketch concept of how the ionosphere is. In principle, it's similar to the lower ionosphere of Earth, but it's much more affected by any external and internal variability than it can be at Earth. And also there is the other biggest effect, which is the heliocentric distance of the orbit. So the difference between the perihelion and the aphelion is longer, so it's more than the distance between Earth and Venus. So this has an effect on the irradiance that arrives to the planet. And I hope you can see that here in this figure. So these are observations for a full solar cycle, for the previous solar cycle. In green, so there are observations taken at Earth, and in red, so there are observations extrapolated to Mars distance. And the axes are different because, of course, at Mars is lower than at Earth. But you can clearly see that sinusoidal variability, which is in addition to the solar cycle. And that sinusoidal variability is simply the effect of Mars orbit. And this is very important because when you see the plasma, so I created this figure when it was my second or third year of postdoc, actually thanks to people here, to Marco. So this is the total electron content measured by Mars Express, by Marsis at Mars, a full solar cycle also. And you can clearly see that the evolution is exactly the same as the irradiance. So because the ionosphere is the layer touching the solar wind, if the ionosphere varies like that, so you can imagine that the solar wind also is going to induce more currents and less currents into the system because of the strength of the ionosphere. But this, moreover, it's not only that, it also affects the other boundaries. And so here on the left, so you can see it's like a sketch of the system, like a different one. But the Bow-Shape, which is the most external boundary, so it will be this one here, the brown layer here. So also thanks to Mars Express, but different instrument of Mars Express, so we were able to measure the position of that boundary. Here, we consider the boundary here a determinator just to always be in the same plane. And this is what we have here at the top. So in blue is the solar irradiance. And in red, we have the crossings of the Bow-Shape. So you can see that contrary to what happened at Earth, which the EUV is not important at all, but at Mars, it really controls everything. It controls also the evolution of where the boundaries are within the system. So this is why we know the basics, but now we need to understand why this is happening. And finally, I mentioned before, like the crystal fields of Mars. This is a nice map taken with combination of data from MAVEN and from Mars Global Surveyor for the magnetometer. So you can see the planet. So this is latitude with longitude, and in colors, so you see the intensity. Yeah, is the intensity of the magnetic field. So the crystal fields are clustered in the southern hemisphere and a bit in the equator as well. But they are quite intense to the point, and this is one of my favorite figures. And it's not because I'm here in Italy, it's because it's really one of my favorite figures. It's a figure that Marco made when I was a PhD student, actually. So this is the total electron content measured by Mars Express in latitude and longitude. And I think you can clearly see the crystal fields in there. So the full ionosphere, on top of everything else, is really depending, it really varies with what happened with the crystal fields. So there are more, how to say, inputs of variability that we could imagine, even if the planet is smaller than any of the other inner planets in the solar system, with the exception of Mercury. So that's for the first goal. For the second goal of the mission, so I told you before, is based on the radiation. And I think there is nothing better to show the radiation than to show the auroras. This is a very large storm that happens in September 2017. There was a very large solar energetic particle event at Mars, actually at Earth as well. And you can see here, so this is the ultraviolet observations of Mars. The full disk, you will see here, and suddenly it starts to glow. So literally, there are auroras. Every time that there is an SCP event, there are auroras everywhere on the planet, like literally everywhere on the planet. So with Maven, this is the best resolution that we can get. But recently, we have an Emirates, the Emirates mission at Mars, and actually we can get more refined observations of what happened. And I'm going to show you this in a bit. You can see that actually the structure of these aurora emissions are much more complex than we can imagine at the beginning. But before that, I don't know if you were lucky to see the auroras last week here in Italy. I took this in Leicester. I went to the countryside and took these nice pictures just with my phone. And you can see that with a simple phone, you can actually take pictures and you can see the colors, right? So this is what we have on MAT. So we have a camera for the visible for the first time, because all the previous cameras, so this observation that I show you here are in the ultraviolet. But for the first time, we are including a camera in the visible. This is because it's a small camera, but also the emissions are predicted to be much more, very, very strong in the green line. So that's why we decided to go for that, because we think there is much more science that we are missing by having ultraviolet observations in the, of this phenomenon. So, but just I put this picture here for air, because at air, so this is confined to the poles, because it's confined because of where the magnetic field is, right? We were lucky last week because there was a big geomagnetic storm, and then the ovals moved towards lower latitude. But otherwise, you just go and see auroras in the northern and southern, very near the polar caps, right? In the oval for the aurora. But on Mars, that's not the case. And there are many types of aurora, and basically Mars is all the time glowing. So there are an astronaut and go to Mars, you will see auroras all the time.
Good morning, everybody. Thanks for being here.
Sorry, can people disconnect the microphones? Okay. So there are discrete auroras, which they were discovered. So these are pictures from Maven, but they were discovered by Mass Express. The discrete aurora happens at the cusp of the crustal fields. So this is like Earth, but just in the southern hemisphere, like in the small. Then we have the diffuse aurora, which is global. So every time that there is a space weather event, the full planet glows. And this goes deeper into the atmosphere. So this emission is like much, much deeper than this one in the atmosphere. And then sometimes, well, or many times, so we have day-side aurora, proton aurora, which is mainly protons from the solar wind interacting with the planet. And they also glow. Of course, the glow cannot be in the visible, because with the light you don't see that, but you can clearly see that with the IUPS instrument. But since a few years ago, actually since 2 years ago, so we have the Emirates mission of Mars, and the camera is better because the orbit is more elliptical, so we can actually get more structure. And I don't know if you can actually see from where you are, but in this picture here, there is a real picture in the ultraviolet. So there are some contours here in the south hemisphere. So these contours are where the crustal magnetic fields are. But you see the emission is actually far away from the crustal fields. And it's like a discrete emission. So it's a discrete aurora, like the one that we show, like the one I show here in this slide. Just even hard to see in here, right? So there are no crustal fields there, we know that. But you see what happened at the tail. So the crustal fields, they rotate with the planet, and they reconnect with the solar wind. Same what happened at Earth with the Tange cycle, but they reconnect all the time. And it's actually impossible for us with a single spacecraft to know what's going on. So we rely in magnetic topology to understand the particles, how they are moving, if they are moving from the day side to the night side, if it's an open field line, if it's a closed field line. The configuration is extremely complex. And that makes that the tail twist. And we see auroras where in principle we should not see auroras. And it has been just discovered last year or 3 years ago. So just to explain you why is that, so there is still a lot of, actually myself, I'm doing research on that, so it's still very new for us. And we thought the night side it will be safer in terms of radiation, but it's actually the opposite. This is where you get the most radiation, and it's simply because of the magnetic field. And this is quite unpredictable at the moment. For Venus, there are no crustal fields, so it's just a nice drape interaction with the solar wind. But for Mars, we have like a party of lines with open, close, open between them, leaving the planet. There is a lot of everything. So maybe that's why also there is more escape at Mars than on Venus, of the atmosphere. It could be many reasons, so this is actually quite new at the moment that we are studying. So we want to focus on that with the mission as well. And this is actually just a paper that was published 2 weeks ago, in which we did for the first time, because it's very, with a single spacecraft, it's very difficult to find the timing to meet with another spacecraft. But there was a nice opportunity with 10 minutes of difference between the Emirates mission, we put this green dot here, so it's the aurora from measured by the Emirates, and in orange and yellow, so we have Mars Express. So it was only a 10 minutes difference, and it's the closest one that we have ever seen that. But we were able to see, again, you can see a rise in the yellow line, which is Mars's electron density. You can see a rise and increase at the time where you see the emission from the aurora. So this is actually the first, very, very first time that we see that of Mars. So we suppose this is happening because it's based on theory and everything, but we have never, until this paper, we have never been able to see that. So there is still a lot to know in here. And all of this, basically this emission is because the atmosphere is absorbing that. So while the atmosphere absorbs that they don't reach the surface. So then it's important to understand how the atmosphere behaves, even on the night side. And just to find out with this second goal, so this actually is more complicated now and it's making my life a bit difficult at the moment, because also like a month ago or 2 or 3 months ago, so the Belgian people working on TGO, they discovered that actually there is a very nice green night glow at Mars, which is amazing. It was this is what you see at Earth, and this is a recreation of what you see at Mars, because of course we don't have a visible camera in TGO, so it's so ESA made this illustration just to show that. But that means, so the wavelength of the green aurora is 557 nanometers, and this is 551 nanometers. So it's in the filter of the camera. So we are changing the filters of the camera just to account for that. First, because we want to have clean aurora observations, but also because we want to measure this properly with a proper instrument, because TGO has a proper instrument, but it has been found like almost recently, and now we want to have like a proper design instrument for that. So this is what we are working at the moment. I'm working on that, and I will go next week to Japan to talk to the people about that. And the last goal, which is mainly the ionosphere. So I said before, this is the coupling with the low atmosphere. And so this is why we are doing this. So it's basically this region in the sketch that I showed before, this region here in green. So we don't have direct observations to start with, but every time that there is an SCP event, so when there are auroras, when there are other stuff going on, like problems with communication, so is this region where the particles stop. And we don't have observations. So the critical region, we don't have observations. So we have especially instrumentation to measure that region for the first time. And specifically also focusing on what happening with the dust. Because you know Mars has global dust storms, so that's famous, right? But this dust storm, so the dust is charged, so we believe it's charged. We move up, and it actually interacts with the ionosphere and produce that the ionosphere move also all the column by 30 kilometers. So there is still a lot of unknowns in here. So actually with the same camera, we can measure auroras on the night side, but also dust opacity on the day side. So it has a very wide dynamic range, specifically to measure that in here. And why I say this? This is actually my own research, which I don't have time to write, but I promise there are no co-authors here, I think. But I promise my co-author I will write a paper soon, but it has been impossible. But that was a very large event, happens 2 years ago. On the top panel, so we have Maven data. So these are energetic particles coming into the system. So ions and electrons. And this is the largest, or up to the moment, it was the largest ground level enhancement of radiation measured by the rover Curiosity at the surface of Mars. So something happened in between. And so why there is this large enhancement? So why the atmosphere did not absorb those particles? So we are doing a lot of research on this. And if you remember my sketch that I showed before, when there are an SCP like the one that I showed before, so they create layers at this angle. So this is the region where we don't have observations. And we have the Marsis radar. And the Marsis radar measures the surface of Mars. But when this happens, this is what we get. So we don't get anything. So by analyzing this mapping in here, you can actually get an estimation of these layers and understand what's going on in there. So this is actually something that is quite relevant for our research, but something that we are going to focus on the mission. And I will go quickly because I think it's a bit late. I will go quickly here. So even if the mission is only focused, it's mainly focused, the goals of the mission are focused on plasma. So we are fully aware that with the instrumentation we have, other people can do science as well. And one of these science is meteorological studies. So we have a group of people who are how to say, working with the capacity of the camera that we have to measure. So these are observations from MRO and observations from mass express, but to measure the winds, how the clouds move, and they can actually do science with our camera. So it's not in the goals, but it's there. So why not? And the same with heliophysics studies, because we will have a solar wind monitor there at 1.5 astronomical unit. So people, okay, so it's not like it will be in L1, but it will be here. So there is a lot of interest from the heliophysics community, and actually we have a working group of people working on that. So going to the mission itself, so we have two spacecraft, which we have called Henri and Marguerite. Henri for Henri Matisse, and Marguerite for Marguerite, which was the daughter of Matisse. And two orbits, so these are different sketches provided by ESA of the different configuration that we have. We are playing at the moment with the orbits to see which one works better for the science. But the nominal characteristics are Henri is the magnetospheric orbiter, so it will have an apoapsis of 3,000 kilometers, which is on average where the bow shock is, and a periapsis of 250 kilometers, so in the ionosphere. Marguerite is the solar wind monitor, so it will have an apoapsis of 10,000 kilometers, and periapsis 250 in principle. And because of orbit evolution, it will actually go to the tail. So it will measure the deep tail, which has not been explored so far, of Mars. And actually, we have, for the first time in another planet, so we have radio occultations between them, like the GPS do at Earth, the GNSS constellation. So for the first time, there will be another planet, full communication between the two spacecraft, providing neutral density, neutral temperature, and electron density of the system from the surface up to where the other spacecraft is. So this is actually I'm quite excited for that, to be honest. So in total, we have 6 instruments. 2 of them are a suite of instruments. So Rafaela and I works on the MEPI, which is the particle suite of instruments. We have an electron analyzer, an ion and neutron analyzer, and solar magnetic particle detector. But also we have another instrument, COMPASS, which is dedicated to fields. So that's to measure the magnetic field, to measure the electric field, to measure electron density with a Lambda probe, and also a QD ion meter, QD velocity ion meter. Then we have separately we have the mass spectrometer, which because we consider to include that in the MEPI suite, but at the end we decided to separate it because that instrument has their own DPU, so it was easier like that. And then we have an irradiance sensor to measure irradiance and also to perform thermospheric observations by solar occultation. Then we have the radio science instrument macro, which is an experiment between the 2 spacecraft, and then the auroral and DAS camera that I mentioned before. So all of them with very high TRL, because most of them, I will say the 90% of them are already flying in another mission, so it's quite safe in terms of maturity for the payload. And because we have 2 spacecraft, there is a very clear improvement with respect to everything that we have at Mars. So if you want to see this in terms of energy, how is the coverage of the system? So hopefully this scheme, hopefully it will help you to understand that. So we have at the left, the lower and middle atmosphere, so the neutral atmosphere. Then in the middle, I included the ionosphere and thermosphere, and I added the energy below, so you can see the energy of the particles. Then we go to the magnetosphere, exosphere, and solar wind, and then we go to the high energetic particles. So if we consider positive ions, so between all the instruments, I try to maintain the color just to give you an idea. The color means the same instrument. So between all the instruments, so we have a full coverage of all the bands. So the same for electrons and negative electrons. Have different instruments to measure different properties. And the ones that are in blue means that there is a new observation. So there has not been that before at Mars. For the neutrals, the same. So we have instrumentation dedicated only exclusively for that, including from the surface of Mars. And the same for the fields. So with the field, so we start with the aurora. So with the aurora and the visible, we'll cover from the middle atmosphere. So this is the diffuse aurora to up in the thermosphere, which is the discrete aurora. So we will have the range of both of them. With the magnetic field, so actually this is pretty nice because we will measure the magnetic field where the spacecraft is, but also because we have two spacecraft, we can actually extrapolate to the surface and measure the currents below the surface, which will be actually quite exciting for that will be quite neat to do at another planet. And then we have the electric field, which is a total new measurement at Mars. So we have the Langmuir probes to measure the currents. And finally, the solar irradiance that we will measure for, which is the energy that is entering into the system. Sorry, it's not finally, I forgot. We are going to measure dust. We are going to measure dust at the surface via the camera with the opacity, but also the impact in the thermosphere. So this is impact on the Langmuir probes of particle dust hitting the spacecraft. So this is our coverage of the instruments. So we had last year the CDF study. So this is the study done by ESA. So some pictures of us, me here with the ESA team, but also this is all the people at the STEC. So I was there 5 weeks while they do the full design. And the message is like there was no problems at all. So everything is feasible within the announcement of opportunity limits. There was no major problems, no major risk, no major anything. So I was very happy. Everyone was very happy, even if the process itself was quite intense, I have to say. But the solution it was nice. So I guess that's why we passed to the phase where we are now. And we have already started the study. So we had the kickoff meeting in February in Paris. So this is the team, so the people who came. I don't know, Rafaela, where you are. Yes. Oh, behind. Okay. Yeah. Everything is ongoing. So we have the payload, the science. We have a specific working group for data optimization. We have system engineering, which actually will start this Friday, and the EMC as well. So we have everything ongoing. So it's only missing the industry, which I've been told it will start at the beginning of June. And there are 2 primes already selected for Hermatis. So everything is ongoing. So I think for now, I cannot say anything else because I think there is no major problem so far. But I would be happy to answer any of your questions if you want. And with regard to the coverage, I'm finishing no worries. With regards to the coverage, so the current orbits that we have, ESA is working on giving some optimization of them, but they're actually quite nice for what we want to do. So here on the left, we have the scheme in simple of the system with colors, and here on your right, so we have the daily percentage of coverage of both orbits. So on top is for Henri, and on the bottom is for Marguerite. Of course, Marguerite has more coverage in the solar one than Henri, but that's because it's designed for that. But we're actually quite happy with this set of orbits. But of course, they will change depending on orbit insertion of Mars. But that's why ESA is working in the optimization of them. But so far, we can accomplish all the goals that we have in the mission with this set of orbits. So this is for the in situ instruments, but for the remote instruments, it's even better because this is the current coverage of Mars Express. So this is 20 years of observations of coverage of Mars Express. So this is latitude with local time. And so every time that the spacecraft is in occultation with respect to Earth, so this is Earth, so there is an occultation and you can get the electron density profile and the neutron temperature profile of the planet. But you can see 20 years of data, and I will show you what this will do. So this is 1 year, the second year, the third year of the nominal mission of the So latitude with day of the year, local time with day of the year, and latitude with longitude. You can see the full coverage of the planet. So we can actually get the 3D view almost of the ionosphere if you compare to what we have at the moment. So it's really like a massive improvement of capabilities. And this is also quite important. So if the mission is launched in 2037, so we will arrive in the next solar cycle in the peak. I don't trust this because I invented this just to know where the next solar maximum will be. But if following our current one, so it will be towards 2037, 2038. So Hermatis will arrive in there. But the key message is like there is no planned mission at all after what we have at the moment with plasma data beyond that. So we will have a gap. And actually, maybe I'm wrong, but I believe there is nothing else for any other planet. So once Baby Colombo and JUICE end, there are no plasma missions for the community, basically. So this is actually our opportunity to continue for us as a community to continue doing science. But moreover, because specifically for Mars, which is where humans are thought to be sent to Mars, there is nothing to measure space weather, which to me is not logic, basically. But there is a need for the radiation environment, that's clear. And there are no missions planned for that. But also, it's essential, when you do plasma, it's essential to have continuous observation. So if we have a gap of 10 years, it's going to be what happened with Venus. Like now we are restarting to restudy everything that was studied 30 years ago because there was a gap with the data. So that's quite important to consider. So that's my last slide, I promise. So this is the distribution of the payload and the distribution of the scientists that we have in the mission. So we are trying to have as much possible people involved from all the countries. So this is the current countries in which we have active participation. There are other countries that have some scientists, but these ones are the ones that are actually like actively participating in the mission. But not only in Europe. So we have an instrument in Japan, which is the Oral camera, and also we have significant contribution from the US as well for different payloads. So this is our current configurations. This is where we are. Everyone is welcome. This is a mission for the community. Everyone is welcome, and especially I would like to, there is payload from here from Nina. If you want to be involved, please talk to Rafaela, talk to Valeria, who is the deputy of Rafaela, and because everyone is really welcome, this is a mission for the community. It's not a mission just for me or for Rafaela, it's a mission for everyone. So please, if you want to be involved, just say that. We will be very happy to have you on board. And I think I will stop here. So I will leave the summary. I think I talked enough today, but this is basically the message. And if you want to know more, I'll be happy to answer any questions, but also if you want to later to know more, you want to have a different participation in the mission, please send to me an email or talk to Rafaela. And again, so we will be very happy to have you on board. So thank you.
Thank you, Beatrice, for the nice talk and the nice idea of mission. Just to say for the people online, I will ask you to raise the hand if you want to give a question so I can manage both from inside and from online. So there are questions from inside.
Regarding this from solar a few days ago, if you are trying to make a pass today, like
Yeah.
part of curious
I will repeat the question for the people online. So Andrea Chiquetti is asking if, because there has been a lot of activity in the last few days and even few months, like a lot. And if we have time to actually check MARSIS, the radar. So the answer is we check the active ionospheric zone, and there is a lot of activity. Like the ionosphere is behaving very unexpected, with extra layers creating very randomly, like not continuously. And so we are analyzing some of them. I think it will take a bit of time to analyze everything because there is really a lot of activity, but there is a lot of promising things. But actually, I have the homework while I'm in here to talk to you to see if the subsurface had blackouts, because I'm sure there will be blackouts in the subsurface, and it will be good to add that as well in the analysis. Yes.
actually now, whether it's no.
I think so. Yeah, I think so. Andrea said that the Marsis is now transiting the south hemisphere where the crustal fields are, and from the day to the night side. So I think it's actually perfect because we know we have also the other satellites helping us to see what is entering, like MAVEN, SEP, and other instrumentation. And we have Marsis in the south hemisphere with both, because I think there is a good coverage between subsurface and active ionospheric zone. So I think we can actually do quite nice science in there, and especially how the plasma is transported in the south hemisphere towards the night side. Which I wanted to do this for a long time, but we did not have the right orbits. But I think these are exactly what we need basically. So maybe we can talk later to see what you see in the subsurface mode.
I'm just curiosity. Of the working activities like this. I was wondering, in terms of the preparation for human exploration, if you explained very well how you learn about the environment. I was wondering, can you from that those data predict what happens on the surface that would be the real impact
Exactly.
of exploration, or it will be in the future rovers correlate what you see?
I mean, the more it's like at Earth. So at Earth, we have like a massive set of satellites outside Earth, within Earth, and also at the surface with the magnetometer network and everything. So, of course, always it will be needed to have. The more you have of Mars, the better. Especially if you have a magnetometer at the surface, or even a small radar at the surface, like just antenna. It will be very simple. But the key for us is actually to understand what's going on in the ionosphere, so then we can start forecasting. So this is basically what happened at Earth in the 70s. So it's like starting all the process again from, with new observations of Mars. This is because, so for example, the data that I show from the rover Curiosity, so it clearly show a very big enhancement of radiation at the surface of Mars. This not happens all the time. So it only happens when there is a big event or when the circumstances allow the particles to go there. So why the ionosphere sometimes allow the particles to pass and others it does not allow them to pass? That is really quite unknown in that region, and it's because we don't have observation. So our goal is to have the best characterization that we can with 2 spacecraft. Because of course, the more you have, the better. But in our case, because it's an M class, so we can only send 2 spacecraft basically. And is to get this characterization to understand why, if I have an SCP event, which is mainly electrons, they produce a lot of ionization. But when there is a proton one, it's not very clear why. While protons have better ionize, they are easy, a particle is more ionized if a proton hit the particle rather than an electron. But still, it looks from Marsis and from the data we have that the electrons are the responsible. So there is a lot of unknowns in there. So our goal is to understand what is happening in that layer and why sometimes the particles can go deep into the surface and why they don't go. So any future mission, even if it's not human, even if it's just robotics, so you will learn from that experience because it's really essential. It's like, to me, it's really like a sponge in the middle of the atmosphere, and why sometimes the particles go and why sometimes they don't go. So it's really like a mystery, to be honest. And I forgot to say that if you have a blackout, so the radar is not working, but that is the main because this is in HF. So it means there is no communications at all. So if I'm back to this slide, so in this situation, in this part where these layers are created, so there is absorption of signal without depletion in there. So that's why when Mars operates, so we know the radar is transmitting, but it's not receiving signal because the atmosphere is absorbing. But this is in the HF. So if there is a satellite communicating with the surface, there won't be communications at all. Because the ionosphere is going to absorb that. So it's not only, I mean, of course, for me, it's scientific, but it has a strong implications for many aspects. It's really a space weather event. It's really a space weather effect, like what happened here at Earth with the grids of the trains, and with the nuclear plants, etc. So it's the same, but in the scale of Mars, because of course there is no infrastructure at the surface of Mars. But imagine this event was in February 22, and it's not the last one. And it lasted, so this is 16th February, and it ended on 21st of February. So for all these days, there are no communications at all with the surface, at all. And you can ask Andrea and Marco, because they thought for many years the radar it was in blackout, and there was nothing to do with that. And then we found like, oh, actually I can do science and I can learn something from that. So it's a big problem at Mars, I have to say. Much more than at Earth.
Yeah, I think that the goal of the study that this year time is also to define the requirements of the instruments.
Yes.
So you suggest how to study, so which kind of model or data can you
Yeah, well, I mean, we're welcome. Yeah. So Anna is asking if, what data or models we are using to, because we have to do all the requirements now of the instruments to measure the science that we want to do. So we have already in the phase 0, we already all the instruments together did like a set of minimum requirements that we need, which are the ones that we are using as a base. But now we are doing two parallel things. So we have the science study team, which is like, there are 9 people, I believe, at the moment, or 8 people, 9, from the different teams, and also people who are not from the teams, but they have good expertise, and we know we can use them. So we are revising everything to be sure everything is captured, but not only from the point of view of an instrument, it's like from the point of view of all the instruments as a whole. Because, for example, you cannot measure these blackouts in here if you don't have, at the same time, if you don't have solar wind observations of what is entering into the system and how is the lower atmosphere and that. So as a whole, we are working on that. So officially, this is done by the science study team, but also all the teams are doing a big effort to have like science sessions just to understand that we are not missing anything and we are capturing that. And also next year, we are going to organize a community workshop for everyone. Is absolutely welcome, like even if people are not from the mission, but we plan to have as much people as possible in order to get the largest return and to be sure like maybe other people who are not involved in the mission, they have good ideas that we can include. So just to capture that. So we are working a lot on that, and it's a very, very important part for us, just to be sure that we are not missing anything.
Thank you for this wonderful talk and wonderful answer. My comment regarded exactly this slide and this kind of studies, because in my opinion, I think it is very important to have these measurements of high energetic particles in these altitudes. But as you already know, there is a long-standing question, for example, for Venus, but I guess it's a similar question also on Mars, in the cloud formation processes.
Yes.
And we know that the
yeah.
cosmic rays or solar energetic particles previous play a role, but we do not know the details.
Yes.
So I think having this measurement there, apart from ionization, helps us also to understand the spallation process details, to understand all this cascade path that produces this kind of release. And if I remember well, in Mars, there was another one in 2021, maybe 28 October, because there was a paper by Jean and So these are rare events, and we have in the chance to have for the first time this measurement on the surface of Mars.
Exactly.
Your measurement will make exactly this link between what we see on the surface, which helps also for exploration, prospect, human space exploration perspective, but helps also for the sun, to understand how clouds are formed and what is the role of the external environment in the planetary environment.
You know, there are some studies from the people in Spain on Mars Springs that it looks like there are some cloud formation on Mars that are related to the crustal fields, which is very, no one has heard that before. But probably these particles traveling through the magnetic fields and maybe producing a base is extremely, how to say, you need a lot of modeling, and it's extremely difficult to know with the data on Mars Express, because there is only the radar and an electron analyzer, and that's it. But that's a very good question. And actually on the payload, so I didn't mention in here, so I don't know if you can see, but there is at the very end, there is an infrared thing in there. So this is because by default, ESA put a radiation monitor on the spacecraft, and we know that because actually I mean, now Valeria can tell because I work with that on Pepi Colombo and on JUICE. But it is very useful. It's not necessary to have that to accomplish the goal of the mission. So if there is no radiation monitor, it's still fine. We can do exactly everything that we wanted. But I know ESA will put a radiation monitor. So that is exactly for what you are saying, for the galactic cosmic rays and for everything else more energetic that is coming into the system. Because we know it charges the dust at the surface. We know it can produce extra ionization very close to the surface, and it can affect the clouds, it can affect the climate. So yeah, exactly, yeah.
When you talk about the evaporation of the rovers, are you going to use the radio link, the rovers and the spacecraft?
Well, yes. So this is very tricky. So Andrea is asking if we are, for collaboration with the rovers, if we are going to use the radio link of the rovers with the orbiters. So in principle, we can do that, but we can only do that with the ESA mission. So for now, because because we work, for example, on Mars Express, so we work with an ESA mission, so they're happy, ESOC is happy to give to us that information of TGO and Mars Express. And we can work on that at the moment to characterize. With NASA, it really implies a collaboration because this is not scientific data, so this is really commanding data. So NASA knows about this, and actually I was 2 weeks ago at Goddard in a space weather meeting with them, and they know about this, and they are willing to collaborate, but it really needs an official collaboration with ESA, otherwise they're not going to give those information, basically. So for MATIS, there is no need to have rovers at the surface. It will be better, of course, and we will get more science, of course. But we have our radio science instrument on the 2 spacecraft, so the 2 spacecraft communicate between them, and then we get everything from the surface. So we are autonomous, let's say. But we have 15 years to convince NASA. And I hope ESA, there will be the Rosalind Franklin rover. So hopefully we will get more information from ESA as well soon when the ExoMars rover is at Mars. But for now, I think we can be autonomous, but of course, the more we can do with other satellites, the better. And because our radio satellite link is in the UHF, which is in the same one as the communication with the rover. So we are also working with the frequency office, which I don't remember. It's an international office, which I don't remember the name now, to allocate a frequency band that we can use all the time. Because if the rovers are communicating with the orbiter, we cannot operate the radio link. So this office, which I don't remember, but it's an international office to allocate frequencies in deep space. So they are going to give us soon a window of frequencies to use, to be totally independent and not to be affected by the rovers. But of course, if there is of course, there will be a relay, so we could also use the relay to get information from the rovers. Exactly. Exactly. I think it's lower. I think it's in the UHF or in the VHF, I think. Right? I think it's 400, 500 megahertz. I think, yeah. The Giga is with Earth, I think. But the rovers with the orbiters is in the 400 megahertz band, I think. Yeah, there is a lot of extra science. Yeah, I think there is a lot of extra science that for free we can do. But the message is that we are autonomous. So even if we don't get this extra free, we can still do everything. But of course, I know, because also there will be occultation with Earth, so we can still do this, the link with Earth for free, let's say. Because the antenna, ESA will send the data to Earth, and we can use that radio link to get the profile as well. But even without that, so we are fully autonomous, and we have the instrumentations to obtain that. But I agree with you, that will be great, because then we'll have observations from more points, basically.
More questions? Okay. So
Well, thank you, everyone.
we can have that.
And thank you, everyone online.